We've already met Kirchhoff's first law, so now we're going to meet Kirchhoff's second law. These two laws are actually really important because they will help you understand everything that's going on in the circuit. If you're stuck, just consider these laws whenever it comes to any electrical circuit questions, and it will really help you out. So Kirchhoff's first law we already met, and it says that the sum of the currents entering any point in the circuit is equal to the sum of the currents leaving that same point. And, as I mentioned in class, this is an example of the law of conservation of charge. Because basically all we're saying is that the number of charges that enter a point per second is equal to the number of charges that leave that point per second. And mostly we apply this when we have junctions. So if you have a junction in your circuit, all the charge that goes into the junction has to come out of it. It's pretty straightforward, but it's really handy for figuring out what currents must be at certain points. So Kirchhoff's second law is all about voltages, and basically it says that for any complete loop, the sum of the EMFs in that loop are equal to the sum of the potential drops round that loop. So when I say loop, I basically mean you can put your finger on the circuit, you start at the power supply, you follow around a set of wires, you keep going, you don't double back on yourself until you end up back at the power supply. That is a loop. And you can have multiple loops inside one circuit. Now this is an example of conservation of energy. It's a very specific example of it because basically we're talking about that the amount of energy per charge we put in is equal to the amount of energy per charge that we get out. It's as simple as that. So those are Kirchhoff's two laws. They are absolutely essential for understanding how electric circuits work. So just to give you an example of what we're talking about here. It's really, really simple, but if we just have a little look at this, if we say that this power supply here is 9 volts, so that means that it's giving 9 joules of energy to every coulomb of charge. And here I have a variable resistor that's using up 3 joules per coulomb, and then I have a bulb that must be using up 6 joules per coulomb, so 6 volts, because everything I put in has to come out. It's as simple as that. You just look at the EMFs, and it has to add up to the potential differences. Now I have said EMFs, so that does imply we can have cells in series. You could have a situation with more than one cell in a power supply, and in that case you need to pay attention to which direction the cells are facing. So if I have two cells like this, I've got a 2.0 volt and a 1.5 volt, and they are aligned together. All I do is add the EMFs up, and I get a total here at 3.5. Next option, obviously, is that I have them the opposite way round. So if I have one power supply pointing one way and the other pointing the other, I'm going to find the difference between them. So the total EMFs is the sum of the EMFs in one direction minus the sum of the EMFs in the other direction. Basically, because if my field is sending these electrons around this way, they're going to have to do work to get through here. So they're going to lose energy because of this electric field. So to find my EMFs, I just find the difference between them. So in this case it would be 0.5 volts in the direction of the 2 volt cell. Now you might see this sort of thing if you have a charging circuit, so where one power supply is charging another. So that's when you'll see it, and that's when you really need to think about which direction things are going. They are unlikely to put the cells directly next to each other in that situation. They'll probably be sort of one on either side, and you have to really think about what's going on and see which terminal is connected to which. So, just to summarise, take a second in your own mind, pause it, fill in the blanks here. All done that? Probably not, but let's give it a shot. So Kirchhoff's first law represents the conservation of charge at a point in a circuit. Sum of the currents entering a point equals the sum of the currents leaving that point. Kirchhoff's second law represents the conservation of energy in an electric circuit, and it says that the sum of the EMFs around a circuit loop equals the sum of the potential differences around that loop. Again, you are going to need to know these, you will want to regurgitate them, but you're also going to want to pull them out when you need to try and figure out what's going on. Okay, and that is our lot. Pretty straightforward, pretty easy. You now have both of Kirchhoff's laws. Good luck!